Good morning, students. In our last class, we discussed about refraction through a prism. So today's topic is some natural phenomenon due to sunlight. Some of the natural phenomena we observe in the topic ray optics, that is due to the sunlight. So in that first one is the rainbow. Next we will study sky appears blue in color. Why sky appears blue in color, and also sea appears blue in color. And next, clouds are white in color. And next, and the last one is during sunrise and sunset, sun appears red in color. So these are the natural phenomena that is due to sunlight. So those are the rainbow, the sky and sea appears blue in color, and clouds are white in color. During sunrise and sunset, sun appears red in color. So these are the five phenomena which are going to study in this chapter. So first we will study the rainbow. So how rainbow happens, or how rainbow takes place. That is, the rainbow is the phenomenon which causes due to dispersion of light. Next, reflection of light and refraction of light, that is refraction of sunlight. The rainbow is a phenomenon which causes due to dispersion, reflection and refraction of sunlight by the rain drops or water drops of the rain. We already know the what is reflection and what is refraction. So reflection is bouncing back of the light to the same medium. That one we call as reflection, and refraction is the that light transfers from one medium to another, or it is bending of light. That one we call as refraction. So we already know about the reflection and refraction. Now, what is dispersion? So dispersion is the phenomenon in which light splits into its color components. Light splits into its constituent colors. That is splitting of light into its constituent colors. If we consider one white light, if it passes through one prism, this one is the white light, that is incident light. If it passes through the prism, after refraction, its color components are splits. That is, the light splits into its color component. The white light splits into 7 colors. That is from violet to red. So that lights are violet, indigo, blue, green, yellow, orange and red. So the white light splits into 7 colors, that is violet, indigo, blue, green, yellow, orange and red. Here the wavelength of the violet light is less than to the wavelength of the red light. That's why it bends the most. So the violet light bends after refraction, the violet light bends the most, and then to the top red light. The red light bends least. So what is dispersion? The dispersion is nothing but the splitting of light into its constituent colors. The constituent colors. The white light splits into 7 colors, that is denoted by VIGGYOR, VIGGYOR, that is violet, indigo, blue, green, yellow, orange and red. These colors called as spectrum. Those colors are called as spectrum. The wavelength of the violet light is less than to that of the red light. So the violet light bends the most and the red light bends the least. So this is about the dispersion. Next, we study how the rainbow happens or takes place by step. So we know that now we know the dispersion and already we know the reflection and refraction. So in the first step, consider one raindrop. So it is in spherical shape. So it is in spherical shape. As light enters, so before going to study this one, conditions. On what conditions the rainbow will appear? So in the condition, first one is the sun will shine at one part of the sky. The sun should shine at one part of the sky. So here we are considering at western horizon. So if here is the sun, so it is at western horizon. So the conditions to see the rainbow or the formation of rainbow, the conditions are the sun should shine at one part of the sky. In the sky we consider sun is at western horizon, and second one is raining will be opposite part of the opposite to the sun or opposite part of the sun in the sky, opposite to the sky, opposite to the sun here. So sun is in the western horizon, then opposite to the western is eastern horizon. So here is rising. So here it is. So eastern part. So next, and the last condition is for the observer, the rainbow will appear when the observer back is towards the horizon. That is, back is towards the western horizon. If we consider observer is here, here is the observer. He sees the rainbow will seen by the observer if the observer back is towards the sun. So observer's back is towards the sun, then only the observer can see the rainbow. So these are the three conditions to see the rainbow. So the first one is the sun should shine at one part of the sky and the raining will be at opposite part of the sun. If we consider sun is at western horizon, then raining will be at eastern part or eastern horizon. Eastern horizon, and observer see, and the observer see the rainbow if his back is towards the sun. That is, sun is behind the observer, then he can see the rainbow. So these are the three conditions to see the rainbow. So next we study how the rainbow will form by step. So consider one raindrop. So it is in spherical shape. As light enters the raindrop, so this raindrop acts as a tiny prism. So this raindrop acts as a tiny prism. That is, as the sun rays enter to the water drop, here the dispersion takes place at this point. Along with the dispersion, refraction also takes place because the sunlight travels from rarer medium to the denser medium. So here if we consider as air, then here the water, the refractive index of water is more than that of air, hence the refraction takes place from rarer to denser medium. As we already say that in the dispersion, the wavelength of violet light is less than to the wavelength of red light. Hence, the violet light bends the most and the red light bends the least. So here, if we draw the normal here, so this becomes violet light and here it becomes red light. Right. So in the first step, as sunlight enters to the water drop at this surface, dispersion and refraction takes place. That is, dispersion means splitting of light. In between red and violet, we have 5 more colors. Here we are considering only the 2 colors for explanation. So at this point, the light, if we consider this point as A, at this point A, the incident ray travels from rarer to denser medium. This sunlight, as already said, this raindrop acts as a tiny prism, then dispersion takes place. Along with the dispersion, refraction also takes place as the light travels from rarer to denser, and the wavelength of violet light is less than to the wavelength of the red light. So the violet light bends the most and red light bends the least. Then, so this one is water drop. This refracted ray acts as incident ray for this surface of the raindrop. This surface, as the light travels from denser medium to rarer medium. So this one is rarer, and here the water drop is denser. Again here it is rarer, medium. So as the refracted ray travels from denser to rarer medium, if the angle of incidence I is greater than the critical angle, here the critical angle is 48 degree. As the denser medium to rarer medium, the angle of incidence is greater than the critical angle, then total internal reflection takes place. That is, light will not emerge from this spot to rarer medium. It gets totally internal reflected. Okay, as the light rays travel from denser to rarer medium, an angle of incidence is greater than the critical angle. Here the critical angle is 48 degree. Then total internal reflection takes place. This is the second step. In the first step, the incident light splits into, that is dispersion takes place along with the refraction. In the second step, total internal reflection takes place. That is because the angle of incidence is greater than angle of critical angle, and also the light travels from denser to rarer medium. Then the red light and the violet light gets reflect. That is total internal reflection takes place. Next, in the third step, the reflected rays, totally internally reflected rays, again incident onto this surface and gets, here also the refraction takes place and it gets deviated, that is from denser to rarer medium, so it is bends away from the normal. Like this. So if we measure the angle between the incident light and to the violet light, so this one is the violet light, it is 40 degree, and incident light to the red light, so it is 42 degree. Okay, here we observe the three steps. Step 3, refraction take place. In the first step also, in the first step, the dispersion and also refraction. In the second step, total internal reflection, and in the third step, again refraction takes place. Next, we will study the primary rainbow formation. Primary rainbow formation. Here we are considering two raindrops. This one is first raindrop, and here it is second raindrop. So as light enters, it gets refracted, and then total internal reflections takes place. If we draw one observer line here, that is parallel to the incident rays, like this. So these are the incident. After refraction, the light rays deviates red, and here it is violet. So the observer is here. So this angle is 40 degree and this angle is 42 degree. So this is the formation of primary rainbow. So in the primary rainbow, the red light of the first water droplet. So this one is the first raindrop and this one is the second raindrop. If you observe here, the red light of the first raindrop and violet light of the second raindrop. Violet light of the second drop will observed by the observer. So observer can see the first, from the first raindrop he see the red light and from the second drop he see the violet light. So the remaining lights, that is violet light from the first raindrop and red light from the second raindrop, is above and below the observer. So if you see the observer from here, he can see only the red light and violet light. So that is red light from the first raindrop and violet light from the second raindrop. Hence, the observer will see the red light on the top, red light on the top and violet in the bottom. So this is the primary rainbow. So primary rainbow, we are considering the two raindrops as the light incident parallelly onto the two raindrops after refraction. That is, first, here also three-step process takes place. So one is refraction in the first step, that is absorption and refraction, and next is total internal reflection, and again it is refraction. So in the primary rainbow we have two refractions, one refraction and two refraction. We have two refraction and one total internal reflection, or it is reflection. So it is a three-step process. For the primary rainbow, it has three-step process. In that, the red light which is seen by the observer, it's come from the first raindrop, and the violet light which is seen at the bottom of the rainbow is by the second raindrop. The remaining, the colors are above and below the observer's eyes. So this is about the primary rainbow formation. So primary rainbow formation is a three-step process. In that, two refractions takes place and one internal reflection takes place. So next is secondary rainbow formation. Secondary rainbow formation. So here also we are considering two raindrops. So this one is the first raindrop and here is the second raindrop. Here two light rays and this one is the observer's reference. From here one refraction, again one reflection, and again one refraction takes place. Refraction, reflection, again reflection, then from here here. If the observer is here, then he sees this one is the red and here is the red. From the first raindrop, he sees the violet light, and from the second drop, he sees the red light. So this one is violet, and here is violet. That is violet light from first raindrop and red light from second raindrop. So here, if you observe the secondary rainbow, compare with the first primary rainbow. In the top, we see in the secondary rainbow, in the top we have violet light, and in the bottom we have red light. But in primary, we have red light in the top and violet light in the bottom. Here, 4-step process happens. That is, here 4-step takes place. That is 2 refraction, 2 refraction and 2 reflection. Hence, the pattern is reverse order to that of the primary rainbow. In the primary rainbow, it starts from red. At the top, we have red color and violet at the bottom. But in the secondary rainbow, we have violet at the top. That is reverse to that of the primary rainbow. That is violet at the top and red at the bottom. So, secondary rainbow is a 4-step process and primary rainbow is of 3 steps. Here we have 2 refractions and 2 reflections. Hence, this rainbow is faint compared to that of primary rainbow, and in secondary rainbow, the pattern is reversed to that of the primary rainbow. So, this is about the rainbow formation, condition for the formation of rainbow and primary rainbow and secondary rainbow. So in the examination, they may ask for 3 marks, either anyone. Either they may ask for primary rainbow formation or secondary rainbow formation. So in brief, we say that in primary rainbow formation, it has 3 steps. That is 1 refraction and 2 reflection. Sorry, 1 reflection, 1 reflection and 2 refractions, and in secondary we have 2 refractions and 2 reflections. Here the rainbow is brighter because it has only 3-step formation. Here the rainbow is faint, that is it is dim, that is dull in color appearance. The rainbow is dull in color compared to that of the primary rainbow formation. So if we draw the angles here, so this angle is 50 and it is 53 degree. If we observe here in the primary rainbow, the incident ray is at the top of the raindrop. The incident ray strikes the water surface at the top, but in the secondary rainbow formation, the incident ray strikes the surface at bottom of the raindrop. So if we consider this one as the raindrop, here the incident ray, that is sun rays, strikes at the bottom of the surface. So this is about the rainbow. So in this, rainbow is the phenomenon. It takes place due to dispersion, reflection and refraction. So rainbow is the phenomenon which takes place due to dispersion, reflection and refraction. Next, conditions for rainbow formation. So what are the conditions? So the conditions are the sun will shine or sun should shine at one part of the sky and the raining will be at the opposite to that of the sun. That is, if the sun is at one part, then raining will be opposite to that of the sun. So this one is the first condition, and raining at the opposite part is the second condition, and third one is the observer will see the rainbow if his back is towards the sun. That is, the observer's back is towards the sun, then only he can see the rainbow. So these are the three conditions for rainbow. So next, primary rainbow formation and secondary rainbow formation. So next topic is scattering of light. Scattering of light. So what is scattering of light? So scattering of light is nothing but changing the direction of propagation of light when it travels or when it incidents on a homogeneous medium. That one we call as scattering of light. That is change in direction of the incident ray when it travels in homogeneous medium. Considering homogeneous medium, that is atmosphere. That one we call as scattering of light. So scattering of light is the change in direction of propagation of light when incident on homogeneous medium. So here considering homogeneous medium is atmosphere. So this is the definition of scattering of light. That is, the light will scatter when it travels in the homogeneous medium. So in that scattering, we have important one is coherent scattering. Coherent scattering. The scattered light, that is the wavelength of the scattered light is same as that of the incident light. That scattering we call as coherent scattering. So coherent scattering means the wavelength of scattered light is same as incident light. So this scattering we call as coherent scattering. Coherent scattering nothing but when the light travels from one medium to another, that is sunlight travels in the atmosphere. After it passes through the homogeneous medium, the sunlight will scatter. That scattered wavelength is equals to that of the incident light. That type of scattering we call as coherent scattering. So example of coherent scattering is Rayleigh scattering. Coherent scattering is also called as Rayleigh scattering. So it is one of the example of the coherent scattering. So what happens in Rayleigh scattering? If the scattered particles, that is, if the size of the scattered particles is less than that of the wavelength of light, that is, size of scattered particle is less than wavelength of light, the size of the scattered particle is less than that of the wavelength of light, then the intensity of scattered light, then the intensity of scattered light is inversely proportional to the intensity of scattered light is inversely proportional to inversely proportional to fourth power of wavelength of light. So what the Rayleigh scattering says means the size of the scattered particles. In the atmosphere we have a particles, smaller particles. If the size of that particles is less than the wavelength of light, then the intensity of scattered light is inversely proportional to fourth power of the wavelength of light. So if we write in mathematical formula, intensity is proportional, that is inversely proportional to 1 divided by lambda to the power of 4. So lambda is the wavelength of light. By using this relation, we are going to discuss why sky appears blue in color and also sea appears blue in color. By using the relation, intensity is inversely proportional to 1 by lambda to the power of 4, that is Rayleigh scattering. Here the size of the scattered particle is less than the wavelength of light. So this is the condition for the Rayleigh scattering. Then only the intensity of scattered light, this is the intensity of scattered light, is inversely proportional to lambda power 4. If we have light, that is wavelength of violet light is less than to the wavelength of red light. As intensity is inversely proportional to lambda to the power of 4, then the lambda value of violet light is less, then its intensity is more. So intensity is more in violet light compared to that of red light. So here intensity of this violet light is more because lambda is inversely proportional to that of intensity. Here the wavelength of red is more than that of violet, that's why here the intensity is less. As light travels in the atmosphere, the violet light scatters the most. Here the violet light scatters the most, but our eyes are not sensitive to the violet light, that's why sky appears blue in color. So our eyes are more sensitive to the blue color but not sensitive to violet color, that's why the sky appears blue in color. So this is the reason. So scattering of light, by using the scattering of light we will discussing the sky appears blue in color. Why sky appears blue in color? As the wavelength of violet light is less compared to that of red, here the relation from Rayleigh scattering, intensity is inversely proportional to wavelength of light. So here the wavelength of light, violet light is less, hence its intensity is more, hence it scatters most. Our eye is not sensitive to violet, hence our eye is most sensitive to blue color, That's the reason the sky appears blue in color and also sea appears blue in color. After the violet we have indigo. This is also the same reason. After the indigo we have blue. That's why blue intensity is more, that is more sensitive to our eyes. That's why the sky appears blue in color and also sea appears blue in color. So next, so the next one is clouds appears white in color. Why clouds appears white in color? So this is the second phenomenon, that is in the scattering of light. Why clouds appears white in color? So the clouds contains water drops, dust and ice crystals. So the clouds contain water drops, dust and ice crystals. So the molecules of these particles, that is the molecules of water drop, dust and ice crystal is greater than the wavelength of light. The molecules in the clouds or the molecules of water drop, dust and ice crystal is greater than the wavelength of light. Is greater than the wavelength of light. That's the reason all the lights are scattered equally. All the lights scatter equally. Hence, the clouds appear white in color. Hence, clouds appear white in color. The main reason is all the lights scatters equal proportional. That is, there is no variation in scattering of different lights. All the lights nothing but V I V G Y O R. All the 7 colors are scattered equally. All the lights nothing but all the colors. All the colors scatters equally. So if all these colors are scattered equally, then it appears in white in color. That's the reason the clouds appear white in color. So the main condition is the molecules which contained by the clouds, that is particles, water drops, dust and ice crystal. All these particles size is greater than the wavelength of light. The size of molecules is greater than the wavelength of light. That's the reason the clouds appears white in color. So next and the last is during sunrise and sunset, sun appears red in color. And the last one is during sunrise and sunset, sun appears red in color. So if we consider here, this one has the earth and here is the earth atmosphere. And this one is the horizon. So sun will rise up here and in the moon the sun is at top above. The sun rays will come from here. The sun rays will come from here. So here if you observe the distance traveled by the sunlight from atmosphere to the earth's surface, that is if the observer is here, the light rays that are coming from the sun through the atmosphere is from here to here. This is the distance traveled by the sunlight in the atmosphere during sunrise. And if we observe the same the distance in the noon time, that is the sunlight travels in the atmosphere, if we compare these two distances, the distances traveled by the sunlight during sunrise is more than that of the noon time. Hence here the most of the light are scattered, that is the wavelength, shorter wavelength, that is wavelength which are shorter or scatters most, that is these lights are removed by the scattering, and the unscattered light is only the red color, and the least scattered is, because the relation we have, intensity is inversely proportional to the lambda power 4. The wavelength of red light is more, hence its intensity is less. If its intensity is less, then it is least scattering. That's the reason during sunrise and also during sunset the sun appears red in color. The distance traveled by the sunlight in the atmosphere is more, hence the shorter wavelengths are scattered due to the scattering, and the unscattered light is only the red color. Hence the red color will appears during sunrise and also in sunset. So this is about the phenomenon, that is sun appears red in color. So this is about the first part of this chapter. So in the next class we are going to discuss the optical instruments. So in the last class we discussed one problem. So the problem is an object of size 3 centimeter is placed 14 centimeter in front of a concave lens, of focal length 21 centimeter. So describe the image produced by the lens and also what happens if the object is further moved away from the lens. So this is the question. In this question we have considered the concave lens, and the given is object size is given, that is HO. They given HO is equals to 3 centimeter, and it is placed 14 centimeter in front of concave lens. That they given the object distance is minus 14 centimeter, and they also given the focal length of the concave lens. The focal length of the concave lens, it is minus 21 centimeter. If it is convex, then its focal length becomes positive. Here they mention the concave lens, hence the focal length we are taken as negative. Next we have to find out the image V and what happens if the object is further moved away from the lens. By using the lens formula, 1 by v minus 1 by u, that is equals to 1 by f, that is 1 by v minus 1 divided by the value of u is minus 14, that is 1 by minus 21. Here minus into minus becomes plus. In the last class some simplification mistakes happens. Here minus into minus it becomes plus. If we shift to 2 RHS, then it becomes minus 1 by 14 and it becomes minus 1 by 21. If we take LCM here, 14, 21, that is 7 2s are 7 3s are, so 6 7s are 42, that is 1 by v is equals to, so 14 3s are minus 21 2s are minus 3 minus 2, that is equals to minus 5 by 42. Then v is equals to minus 42 by 5, that is 5 8s are 40 minus it becomes 20, so 5 4s are 20. So the image distance is minus 8.4. So in the last class we have taken here plus, that's why the calculation goes wrong. So this one is the correct answer, that is v is equals to minus 8.4 centimeter. Next we have to find out the height of the image, that is magnification. M is equals to v by u, that is equals to height of the image to the height of the object. The value of v is minus 8.4. The value of u, that is minus 14, that is equals to hi divided by 3. So minus minus get cancelled. So if we simplify 8.4 divided by 14 into 3, so the height of the image, that is equals to 1.8 centimeter. So this one is the height of the image, and this is the image distance. So what happens if the object is further moved away from the lens? So here is the, consider here is the convex lens. So somewhere here is the object, that is it is 14 centimeter from the lens, and the image is formed at 8.4 centimeter. So this one is the image 8.4. and they given the focal length is somewhere here, it is So the question is, what happens if the object is further moved away from the lens? So here is the object, so this one is the object, this one is the image. This object is further moved away from the lens, the image will reach to the focus and the size of the images goes on decreasing. That is, as the object moves further away, then the image will also move up to the focus, then the image size decreases. As we move the object further away from the lens, then image will move up to the focus, then image size decreases. So this is the solution to the problem. Thank you.